Hi, my name is Tim MacArthur, and today we're going to be looking at correcting for near-surface velocity variation in seismic depth imaging using model move-out or MMO. Processing seismic data, specifically in complex structure settings, we spend a great deal of time compensating for the effects of the near surface on our image. Today I'm going to show a workflow that improves on those traditional methods by incorporating these corrections to our depth model building workflow. So here we have two images, our before and our after. Before uses weathering corrections for the near surface from our time processing workflow. This is our traditional workflow. And after, we are able to update the model based on the improved weathering corrections from our new workflow. So the objective of this workflow is to improve the pre-stack depth migration results from using depth-coupled weathering corrections. The input to the previous migration, our before image, had weathering corrections applied from the time processing workflow. We need to integrate our weathering model and calculate new reflection statics that are coupled to the depth migration. That will produce this after image. So first, let's take a look at an anisotropic PSDM velocity model. This velocity model was constructed using our geologically constrained model building workflow. The velocity range is using this rainbow color map where low velocities are indicated by the cool colors, and high velocities are indicated by the warm colors. The numbers on the display are oriented parallel to the direction of bedding, and they indicate the dip of this velocity model. So what are weathering corrections, and why do we need them? Well, there are differences in weathering layer thicknesses and velocities that cause imaging problems on our subsurface structures. Further, localized irregularities in the near surface also cause imaging problems on our subsurface structures. Our traditional workflow calculates a total weathering correction, which is the combination of the weathering statics and reflection statics. Let's look at those weathering statics. We use our first break picks to create a velocity model of the weathering layer. We then compute time shifts to a base of weathering to account for this weathering layer. So beneath I have an example of a velocity model, a near-surface velocity model calculated from first break picks. And the black line here indicates the base of weathering. So let's look at weathering corrections in a little bit more detail. Here we have a source at our green surface. The source is indicated by a red dot, and a receiver is indicated by the yellow dot. Our source is propagating into the subsurface through the weathering layer, down to a reflector, and back up to the surface. The orange line here indicates the actual ray path that our source travels. For our weathering correction, we assume vertical ray path through the weathering layer. We approximate for the actual ray path, and that's shown by the white line. Reflection statics, the weathering model, does not capture all the time delays caused by the localized anomalies. So we calculate reflection statics by aligning reflection energy across source and receivers. To do this, we use an MMO velocity field to estimate the seismic velocities to align these reflectors. So here are some pre-stack gathers before shifting the traces with reflection statics. Note that these reflection events are flattened by our NMO velocity field. And then here is after shifting traces with reflection statics. So you can see that there's a great deal of event continuity that is gained by applying these reflection static shifts. The only difference between these two images are the time delays applied from our reflection statics. There's still some problems with these weathering corrections. In complex structured settings, the weathering correction assumptions are broken. Velocities in these settings vary laterally, and our weathering layer thickness is not constant. So we have an opportunity in PSDM and depth processing to improve upon these weathering corrections. We can integrate the weathering model into our PSDM velocity model, and we can use this integrated model for move-out corrections and then calculate reflection statics coupled to the velocity model. Here our total weathering correction, weathering statics and reflection statics will be replaced with our new workflow, which uses weathering model and MMO reflection statics to make the total weathering correction. So the first step, we're going to integrate the weathering model into the PSDM velocity model. So if you remember this diagram, by incorporating the weathering model directly into our PSDM velocity model, we're not going to use the statics approximation, but the actual ray path. So here is our geologically constrained velocity model. And here is that same velocity model, the weathering model incorporated into this PSDM velocity model. You can see that there's a lot more cool color, indicating the low velocities of the areas of deposition. Up closely, we can see again the weathering model integrated into the PSDM velocity model. So what does this do to our PSDM stack image? Well, here's our base case image. This is the migration from a final PSDM model from previous testing. And this model has the weathering corrections from our time processing workflow applied. Now, this is using the integrated weathering model. You can see that the stack, there is some areas of improvement, but overall the stack degrades from incorporating this weathering model. So just to review, only using the weathering model degrades the image. Why is this? It's because the reflection statics applied in this case are coupled to the weathering statics and MMO from time processing. So the reflection statics are still coupled to our time processing workflow. Our reflection statics need to be recalculated using move-out correction from our PSDM velocity model. And this is called MMO, or model move-out. So now let's look at our second step. We're going to use the integrated model for move-out corrections, or MMO. Model move-out, or MMO, is the approximation of the move-out velocity field by ray tracing through the integrated velocity model from source and receiver pairs. Here, the MMO travel time is the source plus the receiver travel time. MMO can handle the velocity heterogeneity and anisotropy. MMO applies the move-out component of PSDM. I like to think of MMO as a migration without moving traces. It's a zero aperture migration. So let's look at move-out in complex structures. MMO can properly handle the move-out in complex structures environments. Here we have a simple structure ray path on the left and a complex structure ray path on the right. We can see that the ray path from the blue lines is very complex compared to the diagram on the left. The resulting shot records show very simple hyperbolic move-out in the simple structure. The complex structure shot record shows very complex move-out. So our NMO equation cannot properly flatten the move-out in the complex structure shot, but MMO can. So let's look at the effects of these MMO reflection statics. Here's our step one integrated velocity weathering model into our PSDM velocity model. This is the resulting PSDM stack that we noted degraded. And then here is now incorporating the MMO reflection statics. We can see that the image has regained the imaging in all the areas that it degraded. So to review, all the weathering corrections from our time processing have been removed from our input gathers. Instead, our PSDM velocity model now incorporates the weathering as a velocity. So we've integrated the weathering model into our PSDM velocity model. In our second step, we calculated reflection statics that are coupled to the integrated velocity model. So now we have our weathering correction from our weathering model and MMO reflection statics. Let's compare this back to our base case. So this is the final PSDM from previous testing, and the weathering corrections, the total weathering correction, are from our time processing workflow. And now, here is the PSDM stack image from our revised workflow using the weathering model and calculating reflection statics based on our MMO gathers. We can see that there are definitely differences in the imaging, but there are definitely improvements from our new weathering corrections. So let's highlight some of these areas. These are areas that we have lateral velocity variation in our velocity model. These are areas that we would expect the MMO equation to better flatten gathers through these sections. So on the left, you can see the box on the left, we have reflections that are much more continuous, the new static solution, new weathering corrections, and again underneath the thrust fault and the foreland on the box on the right, we have reflections that are much flatter and more continuous, more in line with the expectation of the structure in that area. So our comparison to the base case shows improvements in areas of lateral varying velocities. However, there are still some areas where the imaging degrades, and I didn't highlight those areas on the previous slides. The reason this is happening is because the current velocity model was built using the weathering corrections from our time processing. So our velocity model itself is coupled to those time processing weathering corrections. We now want to update our model based on the improvements and degradations resulting from the new weathering corrections. The biggest advantage of this workflow is we're able to update our velocity model based on the improved imaging we see from these weathering corrections from our PSDM MMO stack. Here we have our PSDM velocity model with the weathering velocities incorporated, and the reflection statics were calculated from this integrated velocity model. From the imaging improvements from these weathering corrections, we were able to revise the interpretation and update the velocity model. You can see before and after, we've adjusted the horizon boundaries based on the reflection data that we have improved, and then we've revised the interpretation of the fault plane based on the termination of events from these improved weathering corrections. So let's take a look at it on the stack, the PSDM stack. Here's our PSDM integrated velocities and MMO statics. And then here is the updated PSDM stack from that revised interpretation and updated velocity model. Just want to focus in on some of the areas. Again, these are areas that we see lateral velocity variation, where we expect the MMO statics to improve based on the MMO correction. You can see we have better event continuity, the box on the left, and the syncline and fault plane structure on the box on the right have improved more dramatically with this revised interpretation and velocity model update. Further sections, let's take a look at the apex of this anticline. You can see it in the near surface. We've improved the imaging based on these new weathering corrections and velocity model update. Again, the core of the structure is also improved from the improved weathering corrections and revised velocity model. Let's look at the syncline and fault plane more closely. Here's the syncline before with the improved weathering corrections and depth domain, and then again from our revised velocity model. So in summary, including the weathering model into the PSDM velocity model resulted in degraded imaging because static corrections from the time processing don't work with our new weathering correction. Calculating move-out from depth migration travel times created MMO gathers, which we use to calculate reflection statics coupled to the integrated velocity model. So our workflow is now fully integrated to our depth migration. The imaging improvements from this new workflow allowed us to further refine our velocity model, resulting in additional imaging